Thank you very much for the introduction, and thank you very much also for the invitation. So I think I've met some key people of FEniCS at various conferences, not all together. I think the first one was over there, and then Anders and Kent. Oh no, Kent and Anders. So I'm going to talk about a project which is called LIFE. LIFE is basically a rewrite of the kernel of the LIFE 5 project, which is a collaboration between EPFL, Politecnico di Milano, and INRIA. It was written during a European project, which was called e-model or something like that. So while managing this LIFE 5 project, I was not really happy with the kernel, the core features, and it was very difficult to encompass a wide range of methods. We were stuck with very few possibilities. So I started LIFE and from zero again, all over again, and try out some ideas I gathered over the years. So this is the presentation is joint with Gonzalo Pena, who's a PhD student at EPFL and now is in the University of Coimbra. Myself, some people from IFP, the Petroleum French Institute, and Mourad Ismail, also from Grenoble. So basically, what we have is that in scientific computing codes, we have different kind of complexities, right? We have the algebraic complexity, basically large scale, nonlinear, linear, nonlinear system. We have numerical complexity, meshes, numerical methods. We have the model complexity, and we have the computer science complexity. And we need to deal with all this type of complexities, right? And typically, the way you would treat these complexities, that for numerical and model complexity, you would typically use a high-level language with high-level abstraction, typically. Whereas where you need the performance, you would use low-level languages when you need to get close to the machine, to the memory layer, to the CPUs. That would be for the algebraic and computer science complexities. And what I chose for LIFE, this was the core, the most important choice, was to use a new kind of paradigm at the time, which is a generative paradigm. Well, it's available for quite some time in C++. But it was really, I mean, in 1989, it was really very basic. But now it has grown in a very, very, very nice way of implementing software. And I believe that for applied mathematicians, or for mathematicians, these paradigms offer very nice ways of implementing scientific codes. One of the features is that it allows to distribute typically complexity. So on one way, you would have the computer scientist, the developer, that would deal with the computer science and the algebraic part. But totally, the developer would take care only of this part. And then the user would deal on the methodology, the method, and numerical complexity. So just two definitions, which I'm sure you all know. So when I say DSL, it's a domain-specific language. It's a programming or specification language dedicated to a particular domain or problem or solution technique. And in particular, I chose to develop a domain-specific embedded language. That is, it's a DSL which is embedded into another programming language, and here it would be C++. So the thing is that using this generative programming, I decided to do everything in C++. There are absolutely no other languages. Of course, there are external. I have to use external libraries, external tools, because I can't implement everything. I will talk about that later. But basically, you do everything in C++. You have just one language, and inside this language, you have other languages which are geared toward a specific task, and in particular, not only a task but a domain. So the domain would be solving partial differential equation using Galerkin methods. So life is a C++ library. Here is an example of what we can do with life. Just to give a very brief overview, this is a very small snippet of code, but that would be, say, the core part of a Navier-Stokes solver. So this is C++ code. So here you have the deformation tensor. So V, U, and V are vector fields, so typically velocity. When you see T or all, that would define the trial functions with a T when there is a T, and without T that would be the test functions. I need to identify them. So that's not so nice I mean, it's not that easy to identify within an expression where would be the test and trial function. So how I do it is that in the keyword, I identify test and trial functions using suffixes to the keywords. So these are expressions, right? These are expressions. They don't do any computation at all. And then what I do is that I would like to form using the test space XH and trial space XH. They don't have to be the same space, huh? But I write that. And M here is the algebraic representation of the bilinear form that I will write later on. Then I integrate over the elements of the mesh associated with XH. I write here some quadrature formula. At the moment, you are required to provide the quadrature. But then eventually that will disappear and will get computed automatically from the expression if it is not provided by the user. This is something that we can do at compile time to compute automatically the proper quadrature. At the moment, this is user provided, which is good also, I think. You have to know what you are doing. Hiding too many details can be dangerous. And then this is basically OSIN here, what you see. So you will have operator like trans. This is transpose. So you would write here the scalar product of the test function times, or the trial function times the test function. So you would write the scalar product this way. And then the generalized scalar product will be written this way. So this basically is a rank 2 tensor. So you transpose it, you multiply by here the deformation tensor, and then you take the trace. This is the convection term. When you see a V, this is very similar to this operator, except that you just evaluate this function beta, which is basically the convection part. And beta here can be a complex expression which is provided by the user or by, say, a BDF scheme or whatever. I mean, this is this can be itself an expression, and then the pressure velocity terms. To complete the example, if you go to large Reynolds number, you would need eventually to stabilize. And I show here just one possible example of stabilization. If you look at the work by Eric Bourman and Miguel Fernandez in 2007, well, you could add this kind of term here to your variational formulation, and that would read like this, and you need basically to integrate over the internal faces this quantity, which is the generalized scalar product of the jump of the gradient of the velocities. Yes?
What kinds of objects are U and V? Are they, is there some abstract function space class?
I'm going to talk about that. This is just to give what an example of how it would read, the variational formulation would read, how the language would look like embedded in C++. But basically they are functions of finite element space, or function spaces. They are elements of a space, function space.